This is my 16-bit reduced instruction set computer that I made for a computer architecture class. I'm going to run two programs and talk about the design a little bit. So the first program I'm going to run is a multiplication program. This ISA doesn't support multiplication as a machine instruction. It does have addition, so what that means is you need to write a subroutine in software that performs a multiplication through repeated addition. And that's what this first demo program does. So I'm going to program a new bit stream to the device, and this is just going to put the design on the FPGA. And you see the FPGA down here in the bottom left corner. Then open up VS Code. This is where I write the program. This is the assembly for the multiplication subroutine. And the assembler I wrote for this sort of outputs temporary. While it's translating the assembly to machine code, it outputs the native assembly instructions that are supported directly by the CPU and not pseudo instructions, and that's what this is over here in the middle. So anyways, you can see we got a data section and a text section. Data section is going to get loaded into data memory, and the text section gets loaded into instruction memory. And this CPU is a hybrid architecture, so those are two distinct block RAMs. So the first thing the program does, initializes the stack pointer. CPU is a hardware stack, so that's nice. We load two numbers from data memory into registers R1 and R2, and those numbers are 2 and 6. Then we push those numbers onto the stack and jump to this subroutine. And we jump in link, so our return address is going to be stored in register R5. So now we're down here in the multiplication subroutine. We pop those two numbers off the stack, and we basically have a loop that adds the two numbers to each other until the multiplication's finished, essentially. Then we jump back to R5. We don't save the return address because we don't need that. And now we're here. We pop R1 off the stack, which is going to be a result, and we store it back in memory at the answer variable location. Then we halt the program. So I'm going to run it, and you can see it execute on the bottom left over here on the FPGA. So program. You can see the answer is 1100 on those LEDs, and 6 times 2 is 12. 12 in binary is, of course, 1100. So I should probably mention that the bottom 16 LEDs down here display the contents of a register in the general purpose register file of the CPU. And there's 8 of those, and you control which one you're looking at through these 3 switches right here. So these 3 switches are going to be your 3-bit address line to the 8 registers in the register file. You see, I just ran this test program here that loads these immediate numbers into the registers, and you can see that those values are at those locations in the CPU's register file. This also is a good demonstration of the assembler's pseudo instructions, because movi can load a 16-bit immediate into a register, and I only have 16-bit instructions, so how is that possible? Well, it translates to multiple instructions. A load upper immediate followed by a few add i's to get whatever value the programmer requested into that register. So this is the second program that I'm going to show, and it prints hello world. So this program's loaded onto the CPU. The CPU has a UART controller in its memory space, and it loads each character of hello world into a special register in that UART controller. Then it writes another register in the UART controller with a special value that tells that UART controller, hey, you need to transmit whatever is in your data registers. So it first part of the program, we initialize stack pointer, we load the address of the first word of this string, so the H. word isn't 16-bit word, not like the word hello. So we load the H first, or at least the address of it. We push it onto the stack in register R3. We call the send string subroutine right here. And then we pop it off the stack. And we basically have a loop that goes through every address. So it loads each character one at a time. And with each character, it calls the send byte root subroutine with the character that it wants to send on the stack. And then in the send byte root subroutine, it pops it off the stack. It writes it to the special address that has the UART controller's data register. And then it also writes that special value that tells the UART controller, hey, I need to transmit whatever is in my data register. And then we have to delay because the UART controller, it's spitting out bits, it's serializing the data and sending it out 9600 baud, but our CPU is running much faster at 25 megahertz. So we have to wait for the UART controller to finish sending the data to the computer before we can continue sending more characters over. So this is all fine and good, and I'll run it real quick. And on the computer side, I can open it up real quick. You can see that we load the program onto the CPU, and well, first we open the program stored on the computer's hard drive and load the binary into memory, then send that over UART, and then we tell the CPU, hey, the program is in your memory now, and start executing. Then it starts executing the program, and now once the CPU is executing, the Python script switches to reading from the serial port. So it's waiting, it's reading, it's printing out each character that's receiving, and then when it receives 0 as a character, it just kills the program. And this is where 0 is sent. After return from the send string subroutine, we push 0 into the stack and then call send byte, so 0 gets sent over and the Python program knows to stop listening. So we're going to run it. And you can see that's just compiler stuff or assembler stuff. This is hello world. Just to show you there's no tricks going on. We can change that message to whatever we'd like. And load it on the CPU again, and you can watch the CPU's this part of the 7-segment display, these 4 hex characters. That's displaying the program counter, so you can watch it, change really quickly as it runs the program. You can also see these TX and RX LEDs light up when the program runs. So first, TX is going to light up because we're sending the program over. Then RX is going to come on when the CPU is sending data back to the computer. And you can watch them flash. Anyways, so that's this program. So now we're going to talk about the good stuff, the hardware. This is my workflow. Typically what I do is I lay everything out in the block design tool, and then when I decide that I like how it is, I'll go and write the top level module for it, and then add it as in the block diagram as a top level module instead of one of these hierarchies where everything's expanded. That's just so when I change stuff I can do it quickly and kind of see visually what my design looks like. So anyways, that's kind of what's going on with the CPU. So like this whole design, and there's a lot of submodules inside the CPU, but it's just all wrapped in a top level module. And sort of all this stuff around it is the supporting hardware that lets the CPU talk to memory, lets the programmer program the CPU's memory, and lets the CPU send out messages over the UART controller. So probably talk about the programmer first. So when I was loading programs over, through my terminal over Python, through the serial port, this is how the CPU was getting it in its memory. So I have this, basically your UART controller is it's just sitting there and it's listening to the signals coming over, and it's taking them from serial and converting it to 8-bit registers of my received data out. Then this UART programmer is kind of like a control unit that takes the data that it's receiving, and it's got a state machine, and it's like if the 8-bit value just received is program set high, which is apparently 253, and the Python script sends all these special codes over. And this is doing things like setting the program mode line high, so memory knows not to do certain things. Clock enable set high, and this you can toggle the reset line on the CPU to reset it, clear the registers, and this makes it much easier to write programs and debug them because I don't have to sit there and touch the FPGA and hit a bunch of buttons. I just do everything from my computer, and it automatically loads. The LEDs flash. I see the result. I continue doing what I'm doing. And all these blocks, these are just, I'm double flopping the output of this block because the CPU is on a 25 megahertz clock domain and all this UART stuff is on a completely different clock domain. So I want to avoid a metastable condition, so I'm double flopping all my signals and making sure everything's aligned to my 25 megahertz clock domain before it gets read into memory. See, my block RAMs, not only do they have addresses and all the control lines I need for the CPU, but they've got everything I need for the programmer to also write to that section of memory. And then, the programmer flips all the control lines and lets the CPU start cooking on its own, and it goes and executes the program and then halts. So to talk a little bit about memory, I've got my data memory block and my program memory. Programs, of course, stored in program memory, and the data is stored in data memory. Then I also have mapped into the same address space as data memory. I have this UART controller, which also needs to align some clock domains because UART's not going to be on my 25 megahertz clock. And then I've got a UART controller in here, and this sort of has a few registers that the CPU can write through to. But it's, for the address space, it'd be kind of confusing if everything was sort of, had its own address from like a hardware perspective, I guess. So I made this memory controller that, when you write to certain addresses, it takes that address. And like, let's say the UART controller is at hex 400. So if I'm going to write to 400 between these two addresses, I don't want that block RAM and the UART controller to have to think about somehow translating the address from 400 to 0, since the block RAM, whatever logic that Vivado decides to instantiate to decode that block RAM, it's not going to be accounting for a 400 in the address. It's going to be like a 0 or a 1 since it's a small block RAM. So I take that address and I just subtract where it is from the software perspective, and the UART controller, if you told the CPU wanted to address 400, the UART controller ends up getting address 0. So if you want to add more memory mapped modules to the design, you don't have to think about that. You just add them and then make an entry over here in the memory controller. Data memory is pretty simple. It's just a block RAM. Pretty standard stuff. So in terms of the CPU itself and not all the components around it, as I said earlier, it's been put into one top-level module, so I don't really have a nice visual block diagram, but you can see all the components being instantiated, my ALU controller. I do have like an old picture of it before I got rid of it and put it on one top-level module. You can see ALUs, the whole data path. We got a register to store the results of comparisons, immediate extenders, lots of muxes, program counter, stack pointer register file, and of course the control unit. All that's just in here. One cool thing that a bunch of students struggled with in the class that I don't think was covered very well in our previous digital design classes was getting the control unit to act as combinational logic. And what I mean by that is, you've got this control unit, and it needs to be combinational because you're making a single cycle CPU. So it gets the instruction as its input, and it needs to decode that instruction and turn on the control signals to tell certain components of the CPU what they need to do. So the way most people are going to approach that is they're going to use a process block in VHDL or an always block, and more often than not, they're going to make the mistake that they don't cover every possible option. And you have to. It's hard to remember that you're not writing software. You're describing hardware to a synthesizer, so it needs to be able to understand what you're asking it. And when you don't give it every possible combination for every possible input it could get, it starts putting latches in your design, and your simulation results are just going to look bonkers. You're not going to know what's wrong. It's very confusing to figure out what's happening unless you know to look at the post-synthesis schematic. And you can go and see what circuit Vivado decided to create from your control unit. And it'll be really obvious if you messed up, because there'll be certain elements in this design that are not combinational logic. They're not lookup tables. They're sorts of latches or FDREs or some sort of flip-flop. And that's going to be a big red flag because that's not a combinational. It's not part of a combinational circuit that's involving a clock, and you don't have one of those. So it's important. I think it wasn't stressed enough in previous classes that when you design these, you have to cover every option. So your control unit ends up being this long file, and it'd help a bunch of students with that. So I feel like maybe it's important to mention in previous classes that can happen, and you should probably be looking at your post-synthesis schematic to figure out what exactly is going on and not relying too much on looking at the code and figuring out why it's not working from your timing diagrams. So that's pretty much all I've got for the CPU demo. I spent more time than I thought I would have designing the assembler in Python, and it kind of turned out to be a humongous spaghetti code mess. So I'm thinking what I'd probably do differently next time is stick to an ISA like RISC-V, like the actual RISC-V instruction set, and use someone else's assembler and build my own hardware around it. Or maybe stick with my own ISA, but learn how to write a backend for LLVM, or port some other simple C compiler. Really, it's just making sure that I don't have to write the assembler, because that's a big task. So anyways, that's it for my demo.